Hi, welcome to lecture 6.1 on electron configurations. We're going to get an introduction to some of the information needed to understand electron configurations and the very beginnings of actually writing them. We will discuss more of them in class and look at more examples. So take some notes on this so you're prepared for our class discussion. We're going to start off with our Bohr model. So prior to finding out that electrons exist in energy levels, which we now know to be true, scientists knew there was a dense nucleus of positive charge, where protons and neutrons are, and that the electrons surrounded the nucleus. They knew due to Rutherford's gold foil experiment that the volume of our atom was mostly empty space, so the nucleus was very small in the center of it, and that our electrons, which are much smaller than the protons and neutrons, occupy the space around the nucleus, but because they're so small, they don't take up most of it. So our atom is very large, or has a very large amount of empty space. We've made the analogy before in class that the nucleus, if it were about the size of a marble, and we could put that marble on, say, the 50-yard line of a football field, and the atom's volume would be about the size of an entire football stadium. So very, very large atom, lots of empty space. So Niels Bohr came along and would change the idea that the electrons were just around the nucleus, and figure out that electrons actually exist in energy levels around the nucleus. So he actually did some experimenting and began looking particularly at the hydrogen spectrum. So what we can do is take a gas, what's called a discharge tube, and we're going to take a look at this in class so you guys can see in real life what it looks like. Some of you have before last year in chemistry, but we're going to take a look at them as well. So it starts off with a discharge tube, and it has hydrogen in there. So you put this, it's kind of like putting a light bulb into a light fixture, turn it on, and it gives energy. Well, that light was passed through some slits in a board, say a piece of wood or something, so that it concentrates that little bit of light, and then he allowed it to hit a prism. And that prism took that light and broke it into its individual wavelengths. So he could see and analyze what wavelengths of light were associated with that hydrogen gas. We can see this with white light. When we pass white light through a prism, we get a full spectrum. So we get all the colors of the rainbow, or GBIV, as we talked about in class with the electromagnetic spectrum. But when you look at different specific gases or specific elements, they don't have every single light frequency or wavelength associated with them, so they only give off certain colors. So for hydrogen, we get this violet, a blue violet, blue green, and red strong lines on there, 4 lines. So by studying the line spectrum of our hydrogen gas, Bohr was able to figure out that our electrons exist only in certain energy levels or energy states, and he called them the allowed energy states. So an electron in one of these energy states will not be pulled into our nucleus of the atom. It was a concern before his discovery, and a confusing topic, that electrons, due to their negative charge, should theoretically be attracted and pulled into our nucleus, because our nucleus is positive, our electrons are negative, and as we know, opposites attract for charges, and so they couldn't figure out why electrons weren't being pulled into the nucleus. Well, it was found by Bohr that these electrons have energy. So because they have a certain amount of energy, they can stay away from the nucleus and stay in their particular energy level. So he helped to explain that and further our knowledge about the electrons. So Bohr found that not only can electrons exist in energy levels, but they can jump between energy levels. So they can jump from, say, energy level 1 to energy level 2, but they can't be in between them. They can't be in like an energy level 1.5. It doesn't exist. So they can only jump between specific energy levels, these quanta energy levels. So that's why we get these very specific colors. So he was able to see, using our equation that we looked at last week, energy equals Planck's constant times our frequency, that when an atom loses a photon of energy, so it loses a specific amount of energy, the atom will give off a certain frequency of light associated with that quantity of energy. So each amount of energy, E, has a specific frequency of light that is associated with it. So if an atom gave off this for whatever amount of energy it needs, they can create this violet line, or that frequency of light, the 41.0 nanometer wavelength of light. So we could actually go from knowing the energy to figuring out the frequency, and because we also have our other equation, the speed of light equals lambda times our frequency, our wavelength times our frequency, we could go from our frequency to then our wavelength. So it can be, all these things are related to each other. So an amount of energy given off tells us the frequency of light and the wavelength of light that will be produced by that amount of energy. So the electron, the atom, will gain energy. So like, for instance, the electrons in the hydrogen atoms in our tube here gained energy through electricity, and can jump to a higher energy level. And then when they fall back down or release that energy, that's when that energy is released as light. So the energy is released and it comes off in wavelengths of light for specific frequencies or specific colors. So we get these line spectra. The more energy levels an atom has, and the more electrons it has, the more variety in these colors we can get. So each element has its very own signature line spectra. And this is one way that we've been able to analyze the atmospheres of planets on, that are far away from us, from Earth. We can use the equipment attached to telescopes and analyze the spectra of the gases given off that are in the atmospheres of certain planets, and that's how we can actually figure out what's in the atmospheres of places that we've never been. So it's a pretty cool concept that we can identify elements based on their line spectra. Alright, after Bohr figured out that atoms have these specific energy levels, there's more research done by a number of scientists, and more information was found out about these energy levels. So they found that since electrons only gain and lose quanta, or specific chunks of energy, the electrons only exist in specific energy levels. We represent the energy levels with what we call the principal quantum number, which is the letter N. So our principal quantum number is symbolized by N, and the numbers associated or given to N represent the energy level. So for instance, when N equals 1, that's our first energy level. When N equals 2, it's the second energy level, and so on and so forth. As N increases, as the energy level increases, the electrons in that energy level have more energy associated with them. So if you're in energy level 2, you have more energy in your electrons than you do in energy level 1. When all the electrons are in their lowest possible energy level, so none of them are excited, then we call it their ground state. They have been grounded. When the electrons jump up energy levels, they are in an excited state. So you give them energy, they jump up an energy level, then they can release that extra energy, fall back down, and give off light at that point. So these different transitions between energy levels, going up and falling, are where we get those packets of energy and the specific frequencies of light that we give off. So an electron can go from the first energy level to the second, or the first to the third, or the first to the fourth, or the second to the fourth. So you get all these different amounts of energy that can be gained, and as we lose those different packets of energy, we get specific frequencies of light. And we get all those different colors, those bands on the line spectrum. Alright. So, it's great to know that we have energy levels, but how do we figure out which energy level an atom is sitting in and where its electrons are? So we can use, of course, our periodic table to help us. We can determine the energy level by looking at what period an atom is in. So remember our periods are our rows of the periodic table, and that this one's labeled very conveniently. So we have period 1, period 2, period 3, which corresponds to energy level 1, energy level 2, energy level 3, and so on. Remember that this bottom section is not separate. It's not row 8 and 9 of our periodic table. It actually fits. This is lanthanum is number 57, which would come right here in between these two. So we can cut our periodic table in half right here and slip this whole 2 rows right in there. So that's what our periodic table actually looks like. We just move it to the bottom for space-saving reasons. So when we look at this, if we look at hydrogen and helium's electrons, they will be in our first energy level. So hydrogen has 1 electron in the first energy level. Helium has 2 electrons. They are both in the first energy level. If we look at lithium, which comes next, it has 2 electrons in the first energy level, and then its 3rd electron is added to the second energy level. So it fills up the previous one before it adds to the next energy level. As atoms add electrons, they will add energy levels. So as we move, we go from lithium to beryllium, we jump across to the other side, we fill up the second energy level, and then when we need an extra space, we go to the 3rd period or the 3rd energy level. For our ground state of our elements, the 7th energy level is the highest energy level we have. But if electrons are excited, they can jump higher than the 7th energy level, because the energy levels don't exist until the electrons are actually in them. It's just an amount of energy that the electron has. It's not like this place that they're going to. So if an electron is excited, it can jump higher than the 7th energy level. Alright, so we have electrons in energy levels, but these energy levels are not just orbits around the nucleus like the planets orbit the sun. It's not this flat spherical or orbital that we think of it as. We do represent atoms with these flat spherical orbitals sometimes, but it's just because it's an easy model to use to represent specific things about an atom. Not every model is perfect, so we have to add to a model or change our model to describe certain things about the atom. So, trying to picture where our electrons are gets a little bit fuzzy at this point, literally, because we have these fuzzy models. So, we call them probability density. So, if we could take pictures, or if pictures showing the position of a hydrogen atom's electron could be taken and layered over one another. So if we could take thousands and thousands of pictures of a hydrogen atom and highlight where its electron is in each one of these pictures, we would get something that looks like this, where the electron is all over the place. Every time we take a picture, it's moved somewhere else. So it's really hard to find an electron and to locate it and to hold on to it. We can't really do that, but we can see where it's most likely to be. So this is probability. we can tell from this that the probability for our electron in the hydrogen atom is that it's going to be around this center axis of this three-dimensional plane. So we have a kind of spherical shape to our electron and where it's hanging out. Well, we call that area that the electron hangs out, the spherical shape, we call it an orbital. And that orbital is called our s orbital, happens to be called our s orbital. So, the electron is likely to be found in the area closer to the nucleus, but not in the nucleus. The electrons are not as likely to be found further from the nucleus. We can see there's not that many dots out here. The electron density shows the electrons occupy a spherical shape. So that's our first electron orbital. Call it our s orbital. The letter of the orbital shape, unfortunately, has nothing to do with the fact that it's a sphere, but in my head, just so that I can have the letter associated with something, I say spherical is S-shape. But I have found nothing that actually tells me where the letters came from for our orbitals, unfortunately. So I think they just came up with some letters. But the first one is our S shape, and it happens to be spherical, so I think it's a good association. Alright, energy levels and orbitals. So we've got our first orbital here. It's our S shape. Now, as an atom goes up in energy levels, or as it gains energy levels, it will gain orbitals. So we go from having the 1s orbital to the 2s orbital to the 3s orbital, and as we go up energy levels, they get bigger because the energy level is further and further from the nucleus, which is in that very center. So this is the first energy level of the s orbital, the second energy level of the s orbital, and the third energy level of the s orbital. As the energy level increases, it gets further from that nucleus, and the orbitals layer over the top of each other. So you can think of this 2s orbital being like surrounding the 1s, and the 3s surrounding both of those. So it's like having, I don't know what a good analogy is, but it's like having a shell within a shell within a shell. They just keep layering on top of each other. So we can get all the way up to 7 plus spheres all kind of layered around each other. And that's where we would have the probability of finding electrons in each of those energy levels, is in that sphere. Now, the sphere the s orbital is not our only shape, of course. Can't be that easy. We get lots of other shapes. So here I've shown you all the different shapes we can have, that scientists have figured out and we know of. So these depict the different possible orbital shapes and each suborbital within that shape, okay? So this gets a little crazy, so bear with me. We have 4 different shapes, S, P, D, and F. Those are our 4 orbitals. Within those orbitals, we can have suborbitals. The s orbital doesn't have any. It only has one orbital, suborbital. There's one. That's it. The p shape has 3 different suborbitals that, when they're combined, make that entire p orbital. So we have these I kind of think of them as like a peanut shape almost, this p orbital. So it's kind of these 2 balloons hugging the axis, and we have one of them that goes around the x-axis, one around the z-axis, and one around the y-axis. So we get these 3 different shapes to it. When all of those are put together, we call that whole thing the p orbital, and there are 3 p suborbitals. We go to the d orbital next, and as we go from one orbital to the next, we end up needing more space for more electrons. So as we go down, you can see we're adding 2 more orbitals every time. So the d orbital that's our orbital shape is d, and it has 5 different suborbitals. You can tell we got lots of different shapes happening. So yeah, it gets a little bit crazy when we get to the orbital, and then it gets even more crazy. We get to the f orbital, And so all of these put together are the f orbital, but there are 7 different shapes to it, and all put together we make that the f orbital. So it has 7 suborbitals, D has 5 suborbitals, and P has 3 suborbitals. Lots of suborbitals. Each of our suborbitals will make up, when they're combined, will make up that complete orbital shape. So there's a lot to this. Now, each of these, to even more blow your mind, each of these is only one energy level. So you can think of this is our 1s energy level. So first energy level, s orbital. We would have the 2s, which would be bigger, the 3s, which would be even bigger. Well, the same thing happens for our p, our d, and our f. This could be your p orbital of one energy level, and then you go to the next energy level. It has the same 3 things, but they would be bigger. And they would all layer on top of each other. So it builds and it gets more complex. All of these things are layering on top of each other and taking up kind of the same space sometimes. So it gets very intense, very quick. Now, I kind of touched on that already. So not only do our suborbitals combine, but each one has their larger sizes that can correspond to the energy level that we're talking about. So the reason we need so many places to put all these electrons is that each one of these suborbitals, every single one of these shapes, will only hold 2 electrons. So no matter how complex it goes from being a sphere to this crazy shape down here with the f orbital, it will still only hold 2 electrons. So we have elements up to, 115. So divided by 2, we need over 50 plus orbital shapes to hold every 2 electrons that we add. So there's lots of space we need to put electrons in. We need lots of rooms to put them in. So we gotta have a lot of orbitals. So it's all the crazy shapes. Now, it looks insane right now. What we're gonna really hone in on here is how do we know where the electrons are going? What's their address? How do we put them in their bedrooms, kind of thing. So I kind of think of electrons excuse me, electrons adding to their orbitals, kind of like writing an address or putting them into their homes. So, the order that the electrons are going to fill up their orbitals is determined by an atom's position on the periodic table. So, let's just take a look at our periodic table. This periodic table has been color-coded for our orbitals. So it has been found that when an atom adds its last electron, the last electron, depending on where it is on the periodic table, follows a pattern. So for instance, all the atoms on this left side in the alkali metals and alkali earth metals, if we throw helium over here, all of those, their very last electron that's added is in the s orbital. Now that s orbital depends on what energy level we're in, so we have 1s, 2s, 3s, 4s, and so on. Excuse me. But that last electron will end up being added to an s orbital. Same thing over here. We have our p orbital. The very last electron added for every single element in this block, it happens to be added to a p orbital. So we found these patterns to their electrons and where they're being added. So we have our p orbital, our d orbital, and our f orbital. We call each of these sections on the periodic table by that orbital shape, and we call it the s block, p block, d block, and f block. So we kind of block out our periodic table based on those orbitals, and it helps us figure out where the electrons are adding. So the order the electrons fill up the orbitals is determined by their position on the periodic table. The orbitals are associated with certain sections of the periodic table, as shown in our picture. An atom's last electron will be in the orbital associated with the elements placed on the periodic table. The atom will also have electrons in each of the orbitals that come before it. it is important to remember that neutral atoms have the same number of electrons as protons, which is determined by their atomic number. So when we need to figure out how many electrons something has, we look at its atomic number. If that's a neutral atom, that's going to be its number of electrons and protons. So let me give you an example. If I wanted to figure out what orbitals were filled up for a particular element, we would start by finding that element on our periodic table. So for instance, I know that the element right here on my periodic table is aluminum. I happen to know that. So aluminum, its last electron that's added is in the 3p orbital. So 1 electron there. Every single orbital that comes before that, so we look at every atom coming before that, is going to be filled up with its electrons. So we go straight across here. The 3s orbital would be full. Going back, it would be the 2p orbital would be full. The 2s orbital would be full, and the 1s orbital would be full. So we would have electrons in all of those till we get to aluminum, and that would be the last one it fills up. So this pattern, if you go in order on the periodic table from one element to the next in their atomic number order, you can see what orbital is filling up for that atom and which ones it's already filled, which is pretty interesting. So there is a pattern to this. There's a way of figuring it out. Let me show you a couple of examples. So that we can write their electron, what's called an electron configuration, and just kind of like an address of our atoms. So for instance, hydrogen is the element here. It has the 1s orbital, and there's 1 electron in it. This exponent up here tells us how many electrons are in that orbital. So 1s orbital with 1 electron. Well, hydrogen only has 1 electron, so that's all it needs. When we go to the next one, helium is this number 2 on the periodic table, so it has 2 electrons. So it's going to fill up and pair up that second electron for our s orbital. So we get first energy level, s orbital, 2 electrons. Helium's good. Then we go to our next element, second period, lithium. Well, lithium has 3 electrons, so it has to fill up the 1s orbital with 2 electrons, and then it can add an electron in the 2s orbital, and it gets 1 of them. Then beryllium would be next, and it would pair up that 2s orbital. So we had a 1s2, 2s2. So these exponents at the top, if you add the numbers together for all the exponents, you will add up to the number of electrons for that element. Alright, I'll go to another one. So going straight from 2s straight across the periodic table, we come to boron. Boron has the 1s orbital full, 2 electrons, the 2s orbital full with 2 electrons, and then its last electron is added in the 2p orbital. So we have 2p1 at the end. I skipped a few in between. You can think we'd have boron, and then carbon be 2p2 at the end, and then, let's see, carbon, nitrogen be next, and it would have 2p3, and then 2p4 for oxygen, and then 2p5 for fluorine down here. So we have our 5th electron. We could have 2p6 for neon would be our next one. So neon would be our 2p6, and it would fill up that orbital. Once an orbital's full, and remember, this is our 2p orbital, so it's got those 3 different sub-levels. So if you notice, it's got 6 electrons that can be filled up in this row. That's because there are 3 suborbitals, each with 2 electrons. Then we can go down to our next row to sodium. Sodium would have that 1s orbital full, that 2s orbital full, that 2p orbital all the way full, and then we get to that 3s1 orbital. So it does follow a pattern. It's following our periodic table. It's following number patterns with how many electrons are going in each orbital. So we can look ahead. If we look at the d orbital, it has, if you count, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements across, which means for every element we're adding an electron. So we can add 10 electrons in the d orbital. And if you remember to our previous picture, there are 5 different shapes to the d orbital. 5 shapes, 2 electrons each, it's 10 electrons. So the math makes sense. Now you will notice that the numbering seems weird when we get to the d orbital. We are in, according to our s orbital, first energy level, second energy level, third energy level, fourth energy level. Well, why is this labeled 3D, 4D, 5D? It's off by 1. That is not a mistake. It has been found that because when we get to the d orbital, our electrons, to keep our atoms stable, our electrons actually have to be added to a lower energy level. Instead of staying on that outer energy level, that outer shell or orbital, they get added to an inner energy level. So, because they're getting added inside and not on the outer energy level, we have to label it as the 3d orbital, not the 4d orbital. And this is why those transition metals in the middle of our periodic table have such issues, why they can have multiple charges, why they can lose different amounts of electrons, why they don't cooperate in certain situations and bonding and all kinds of things. It explains so much because they can lose different amounts of electrons in different places. So it's not always about their valence electrons when they're losing electrons. It's sometimes they're losing inside inner energy level electrons, or gaining, and it's very odd. So this d orbital can explain a lot about the behavior of our transition metals and their stability. The other thing that's very interesting that can be easily explained by electron configuration is valence electrons. Valence electrons, remember, are the electrons in the very outer energy level. If you think about it, even if you add electrons, so say, pick an element over here. So we have fluorine, bromine, no, chlorine, bromine. So this element right here in the box would be bromine. So bromine would have every orbital coming before it. So its last stuff it would be adding would be 4s, and then 3d, and then 4p. Well, its valence electrons are the ones in the outer energy level. So the 4s and the 4p are the outer energy level. If you add those electrons up, you've got 2 over here, you've got 6 total over here, you fill up the whole row, that's 8 valence electrons. No matter what element it is, it can only have up to 8 valence electrons, even if it has electrons in the d orbital, because they are at a lower energy level. So for instance, bromine has 7 valence electrons, which corresponds to its group 7a marking on the periodic table. It would gain an electron to be like the electron configuration of its noble gas, to be happy. So it explains so much, this d orbital. It's pretty awesome. So our electron configurations do have a pattern they follow. We're going to do much more examples in class on this and explore this more, and do some different diagrams and stuff for it. So, sorry, I went off on a tangent on that a little bit. So in class, we're going to explore more electron configurations, look at lots of examples. We're going to look at orbital diagrams, and those can help us in writing the electron configurations, and kind of just wrap this whole thing up with the electron configurations. We'll also look at, because if you can already probably imagine, as we add more electrons, those electron configurations get much longer and longer, and we'll look at a shortcut for writing them, so that you don't have to write 1s2, 2s2, and so on for every single element. There's a shortcut, or shorthand way of writing that. So we'll take a look at that in class next week. Alright. Have a great evening.